Bueno, buenas tardes a todos y bienvenidos a este acto de lanzamiento de la web TV Campus do Mar, que vamos a celebrar hoy. Esta web TV Campus do Mar se integra dentro del Campus Digital del Mar, que se plantea como una plataforma para proveer a los participantes, a los integrantes del Campus del Mar, de un espacio digital que apoye a su labor investigadora, docente, de transferencia del conocimiento y sobre todo de internacionalización. En ese sentido, el Campus Digital del Mar va a plantear varias herramientas. Vamos a contar con, por supuesto, con herramientas de videoconferencia avanzada. Se va a contar con espacios digitales para el almacenamiento, la estructuración y la distribución de documentos, y sobre todo con esto que estamos hoy lanzando, que es la web TV. En esta web TV, Campus del Mar, van a desarrollarse diversas actividades, fundamentalmente pues, la emisión en directo vía internet de conferencias, de cursos, de tesis doctorales, de congresos, y también vamos a contar con una biblioteca en la que todos estos documentos digitales y otros que puedan resultar de interés puedan estar disponibles a la comunidad nacional e internacional en todo momento, online. Hoy vamos a inaugurar esta web TV, la vamos a inaugurar a través de una conferencia que va a tratar dos temas que nos resultan clave, la comunicación y el mar. Y pues tenemos una conferencia muy interesante con una persona pues, de altísimo nivel y que vamos a presentar a continuación.
Thank you, Ms. Vice President, and good afternoon to everybody. It is my pleasure to welcome you to this inaugural talk of the Campus del Mar Web TV, in which we have the honor to have Professor Milica Stojanovic as a speaker. And she is one of the world-leading researchers in the area of underwater communications. Professor Stojanovic graduated from the University of Belgrade in 1988 and received a master's and PhD degrees from Northeastern University in Boston, Massachusetts in 1991 and 1993. After a number of years with the Massachusetts Institute of Technology, where she was a principal scientist, she joined the Faculty of Electrical and Computer Engineering Department in Northeastern University, where currently she is an associate professor. She is also a guest investigator at the Woods Hole Oceanographic Institution, which is the largest private nonprofit ocean research, engineering, and education organization in the world, and a visiting scientist at MIT. Professor Stojanovic is an associate editor for the IEEE Journal on Oceanic Engineering and for the Transactions on Signal Processing. And she is also a member of the IEEE Ocean Engineering Society's Administrative Committee. Professor Stojanovic's work in the field of underwater communications provided the first feasibility proof of bandwidth-efficient acoustic communication and created a strong impact on the current research in that field. At present, she works on several problems in this area, ranging from the fundamental capacity analysis of acoustic networks to specific signal processing methods and network protocols. She also participates in the development of a micromodem for Woods Hole Oceanic Institution, a software-defined acoustic modem for MIT, and an underwater acoustic network simulator also for MIT. The title of her talk today is Underwater Wireless Acoustic Communications. I already had the pleasure to attend one of Milica's plenary talks in a congress in Perugia about 1 year ago, and I must say it was very, very enjoyable. So it's pretty safe to say that today we all are in for some very pleasant time. So without any further ado, please, Milica, the stage is all yours.
Thank you very much for such a wonderful introduction. Let me just toggle this. Here I will be showing some pictures as we go along with this presentation, and I like sometimes to begin this by just letting the people look at this slide and read the words by one of the greatest inventors of all time, and also to note when this was said, in 1490. So let us move on and fast forward to slightly more modern times. And perhaps ask as the first question, why would we want to do underwater wireless communications at all? Who cares? You know, we have our cell phones on the ground, and who would we be talking to underwater? As a first example of an answer to that question, I like to offer the case of the Titanic. We all know what happened to Titanic and how popular it became. And people have known for a long time when and about where Titanic sank, but have never really set eyes on the Titanic until relatively recently in 1985, when a team from the Woods Hole Oceanographic Institution went there with a submersible, as we call it. It's shown in this blue picture here, called the Alvin, which is a relatively large submersible that is connected by a cable to the mothership, and it also had another remotely operated smaller vehicle on it, a Jason vehicle, that went down to the very deep bottom of the ocean and actually for the first time identified, touched, so to say, the remains of Titanic. This is very precious equipment, submersibles, and they have also been used in the past to do other great underwater exploratory work. In this figure here, we are looking at, oh, what have I done now? We're looking at a picture of something called the black smoker. The black smoker is a hydrothermal vent, a source of very hot, I apologize, I have no idea what happened. A source of very hot water at the bottom of the ocean, where, again, for the first time, researchers went with these submersibles to identify what is going on. And what they have found were actually new forms of life. When I say new forms of life, at least when I was a high school student, we learned that there were two forms of life. Well, they discovered a third. I don't remember quite well what these forms were. I never studied biology much more. Anyways, these submersibles, or the remotely operated vehicles, are excellent tools for exploration, but the fact is that they are tethered by cables to the mothership. They receive their power through the cable, and they communicate their findings through the cable back to the mothership. This allows them to communicate at a very fast bit rate, but it also restricts their range of operation to a certain degree because these cables are extremely heavy, and if you're going down to several kilometers depth, they could weigh several metric tons. So the question became, what can we do to get rid of the cables, to dispose with cables, to transition from the so-called remotely operated vehicles to the so-called autonomous underwater vehicles. And here, this yellow torpedo-like thing in the bottom picture is an autonomous underwater vehicle, or an AUV, as we call it for short. And of course, here next to the vehicle is a picture of me, which I like to put here because this is as close as I will ever get to the movies, such as Titanic. Anyways, the point of what I'm trying to say is that the answer to the why question is that there are many things we would like to do in the ocean if we were able to do that using instruments, robots, and vehicles that are not tethered, that are free to move, because of the weight, the cost, and the complications that come with heavy cables. In order to do that, these instruments and robots need to be able to communicate wirelessly either to the human operator on the surface of the ocean, or, as we will see later, in a network setting, to one another. The applications are many, and they are in fact growing as we, the engineers, managed to demonstrate an ever-increasing capability of wireless underwater communications and autonomous systems. The applications include ocean monitoring for climate or pollution recording, for prediction of natural disturbances, also industry, deep sea oil drilling, aquaculture or fishing industry, and so on and so on. There is, of course, underwater exploration just for its own sake, for marine archaeology and perhaps new forms of life, natural resources. And finally, the obvious application of search and survey missions for finding shipwrecks, mines, and so on. So if we're happy with the why question, or rather with the answer to the why question, then the next question we must ask is, okay, how do we do that? The usual suspects are the radio waves, the optical waves, and the acoustical waves. As it turns out, the radio and the optical waves cannot travel through the water except over very, very short distances. Radio, perhaps over several meters. Optical signals in the optical band region, blue-green is the best one to use, can go a little farther, but still not beyond about, let's say, 100 meters. This is not to say that these methods should not be used. They should be used, and by all means, if your application calls for only such short distances, because then they will give you a very, very large bandwidth. But if you want to transmit information over anything but short distances, then you are forced to go to the acoustical waves, like Leonardo did, and to live with what you have. And what you have is a channel that has very poor quality and a bandwidth that is extremely limited. When we talk about high bitrate systems in acoustics, we're talking about perhaps tens of kilobits per second, at which point many of the radio students start to laugh, but such is life. These are high bit rates for acoustic communications. So what has been done so far in this area? Acoustic communications, in fact, date back to older times. Somewhere at the end of the World War II, a telephone system meant for the use by submarines was developed in the United States, and this system is still in operation. It uses analog single sideband modulation in the 8 to 11 kilohertz band. After that, however, we are ushered into the age of the DSP technology, which offers great processing power at remote distances. And here is where we start to see the development of today's modern acoustic modems. In the 70s and the 80s, we saw the development of modem based on non-coherent modulation and demodulation technique. These are still in use because they are very robust, give you reliable performance. And in the 90s, we have seen the development of more bandwidth-efficient modulation and demodulation methods, namely the phase-coherent modulation methods, which have by now also made it into more than prototype modems, into the modems that are actually being somewhat routinely used even on underwater vehicles. And this is what I will be talking about, the technology that goes in, or the science and technology that go into the development of these modems. What is next? Next stage in the development is more signal processing and, of course, integration of acoustic links into communication networks. So here is a little overview of what I will be talking about. I will first talk about the communication channel, the acoustic communication channel, which I think is the most interesting part for those of you who are young new students and perhaps want to join this area, because this is what really tells you about the physics of propagation and opens a path to what are the problems that we have. And then from there, you can start talking about solutions. I will talk about signal processing then, focusing on modulation and detection briefly, not to bother those of you who are not experts in this field, just to outline for you what we have today and what are the current capabilities in terms of the bit rates and distances that we can cover using acoustic underwater communications, which are related, by the way. The longer you go, the less bandwidth you have, as we will see shortly. And I will conclude finally with mentioning some implications of the channel and propagation on the design of future acoustic networks. So let us start talking about the channel. the first things that always have to be said about a certain communication channel are what are its path loss or attenuation, large-scale deterministic attenuation, and what are the noise properties. Because these two things, the attenuation and the noise, define the single most important figure of merit for the design of any communication system, and that is the signal-to-noise ratio. So if you look at this yellow box, it tells you what is the attenuation as a function of distance x and frequency k. And here is the first point that we have to note as the major difference between the radio wireless systems and the acoustic wireless systems. Here, there is heavy dependency on the signal frequency of the attenuation. In radio communications, as you have learned, the attenuation usually goes as distance squared or distance to some other path loss exponent, which is usually a number greater than 2, something between 2 and 6 maybe. Here we have the same effect. This number k denotes the spreading factor, and this is usually between 1 and 2 for an acoustic system. But here we also have this other part, which is A of f, the so-called absorption loss. Absorption is the transfer of acoustical energy into heat. It depends on the frequency, and in this expression it gets raised to the power that is equal to the distance. Pardon me. I'm chasing my arrow, but here's my arrow. There is an empirical formula that can be used to show how this absorption figure changes. And if you zoom in here, you will see that the attenuation here is really, really very large and increases with frequency. So moving on from there, we go to the question of what are the noise properties in this channel. On the bottom left is shown the picture of the power spectral density of the so-called quiet deep sea. What does it mean, quiet deep sea? It means somewhere deep in the ocean where there are no disturbances coming from shore. There could be banging on the shore. Banging is an acoustical signal, and that would cause extra noise in your system. So this is the noise that is observed if nothing else is going on. The various curves on this graph correspond to the various values of the wind. The wind causes waves. The waves break, produce sound. That increases the noise. And the so-called shipping activity, which is a number that models the amount of noise that comes from distant shipping, not from nearby boat coming close to you and producing a large specular source of noise. No, from any distant ship. It is estimated that at any given time there are more than 1,000 ships present around the Atlantic, for instance, and together these ships cause the background noise. Whatever the curve is, whatever the wind speed or shipping activity, what we notice here is that the power spectral density of the noise is decaying with frequency. This is in stark contrast to what you've learned in school about the additive white Gaussian noise channel, where the word white means that the power spectral density is flat. It's a constant, so independent of frequency. Therefore, here we have a channel that is not introducing white but colored noise. Whether it is Gaussian or not depends on the noise source. Many sources can be considered Gaussian, but not all of them. In addition to this noise that is omnipresent, there is also, of course, the site-specific noise that depends on whether you are in an Arctic region where the ice is cracking or near a busy marina where there is lots of banging going on the shore, and so on and so on. Well, if we put the 2 and 2 together, the path loss and the noise, we come up with the signal-to-noise ratio, which is the ratio of the two. And in a narrow band of frequencies, delta f, say, we see that this signal-to-noise ratio depends on the what we call AN product. product between the attenuation and the power spectral density of the noise. The figure in the top right corner shows the AN product, or rather the inverse of the AN product, which is directly proportional to your signal-to-noise ratio, as a function of frequency given here in kilohertz. The various curves on this figure correspond to various distances between the transmitter and the receiver. And if you pick one of those curves, you see that there is a point where it reaches a maximum. On the x-axis, that will be the point where you want to center the operational frequency region of your system. So if you are looking at this curve, here is where it reaches the maximum, and on the x-axis you reach something like 6 kilohertz. You can also put a bar, lower it from the top, and pick a range of frequencies in which the signal-to-noise ratio will be above the bar. This is your operational range. If you look closely at the figure, you will notice that for any considerable distances, we're talking about bandwidths that are on the order of a few kilohertz. So very, very limited bandwidth. The bottom figure shows the optimal center frequency as a function of distance, and you see how it decreases. Together with the center frequency, the bandwidth will be decreasing as well. And here are these letters that say UWA equals UWB. What I mean by that is that underwater acoustics is ultra-wide band. The strict definition of a wide-band system is a system in which the bandwidth is not negligible with respect to its center frequency. That is not the case in radio systems, even when they are called ultra-wideband. That is the case in acoustic systems, which have very limited bandwidth. So within this limited bandwidth, we have to design our communication system. The next question that we want to ask is, how does the sound propagate? There are many answers to that question. What I have drawn here on the top are two charts. One is showing C, the propagation speed, so how fast the sound travels, as a function of depth, and the other is showing a cross-section of the ocean, where we have land and sea. Here we have land and sea, and this is the cross-section of the ocean that has continental shelf, continental slice, rise, and finally the deep depths. As the depth varies here, so does the propagation speed of sound. In the beginning, it is more or less constant. Then it starts to decrease because the temperature decreases rapidly, but the pressure remains more or less the same. Then it reaches a point where it is minimal, and after that the temperature stays constant, but the pressure increases, causing the sound speed to increase. These observations are important for understanding how the sound propagates in deep water, which is shown in the bottom right corner. If you launch a sound ray from a certain depth, because the sound speed is not constant, there will be refraction. The sound ray will always want to turn back to the point where its propagation speed is lowest. It is lazy, in other words. So if I place a source somewhere at some depth, and I go away and place a receiver at any point in this channel, let's say here where my arrow is standing, what I'm going to see is not a single ray of sound, but multiple rays. This is how multipath phenomenon is created in deep water. We observe multipath signal arrivals even though there are no reflections of the surface or of the bottom of the sea. In the figure, on the bottom left corner, you're seeing the usual situation that you may have studied in geometrical optics in school, where you have very well-defined reflections of the top and of the bottom. This is indeed the situation that corresponds to sound propagation in shallow water. Shallow water, if you look back at the picture of sound speed, means that the sound speed is pretty much constant over here, and therefore there is no ray bending. The rays stay flat and they bounce off the surface and off the bottom that are very close in shallow water. So we again get the multipath effect. Typical values of the multipath spread, or the duration of the time over which we receive the echoes, is between 1 or 10 or sometimes even 100 milliseconds. Now, on top of all of that, the channel is not fixed. This picture of multipath formation will not always be the same. Think just about the varying surface. As the waves are forming, the surface is tilting, the multipath arrivals are changing. And what we see at the receiver is a channel impulse response that is slowly varying in time. Sometimes more slowly, sometimes less slowly. There are various mechanisms that are responsible for these changes. I mentioned surface motion, but there are also internal waves, turbulence, and so on. If you're not an acoustician, but a signal processor like I am, you might want to just look at the channel responses that you get from a certain channel. What I'm showing in this picture are the results of experimental channel recordings taken in different places. There is deep water here, there is shallow water here, there is another shallow water experiment there. If you read this later, you will notice that the distances are different, but in any case, we obviously are dealing with a multipath channel that is time varying. Let us take a look at this picture, for instance. If you take a slice along this delay axis, you will get a channel response, an impulse response at a particular moment in time. If you now take another slice, as if you were cutting hamon, you will take a picture of another impulse response, and they are obviously time varying. In radio communications, there is a similar situation, and people know very well how to model statistically this time variation. We talk about Rayleigh fading with a Jakes power spectrum. In this channel, in the acoustic channel, unfortunately, we do not have any widely accepted statistical channel models. And that prevents us from rushing to various conclusions using computer simulation. Instead, we oftentimes have to deploy the equipment and actually measure the channel and see what is going on in an experiment. Here is an example of how we did one experiment. In the top right corner is an illustration of the experimental deployment, which occurred here in the North Atlantic, close to where I live. We place a transmitter at some depth, we place a receiver at some depth, we transmit the sound, and we record the received signal. We can also do some modeling of reflections in this shallow water channel and come up with a frozen in time picture of how the multipath structure will look like after the signal has reflected off the top and the bottom. Then we can predict the channel response, but finally we go out and measure this channel response. And here are plotted, one on top of another, a number of signal reflections. If you zoom in on each of them in time, you see that there are some that are slowly varying and some that are more rapidly varying. And the receiver design will have to deal with this type of channel variation. Another type of channel variation is what is caused by motion in the system, by the relative motion between the transmitter and the receiver. And this is known as the Doppler effect. You have studied that in school. If things are moving towards one another, there will be increase in frequency and vice versa. So basically what happens due to motion is that the time axis gets scaled and the frequency axis gets scaled. If we transmit a tone at frequency f, we will receive a tone at a different frequency, something that is shifted from the original. This is called time dilation and compression and frequency offset, which account for the Doppler distortion. In an acoustic channel, the Doppler distortion is particularly severe. If you look at the numbers for typical velocities and take into account the fact that the sound propagates at a very low speed, very low compared to what? Very low compared to the speed of electromagnetic waves. They go at 3 times 10 to the 8th meters per second. We go at about 1500 meters per second. There is a difference of 5 orders of magnitude. This accounts for very high values of this A factor, of the Doppler factor, which is the ratio between the velocity and the speed of propagation. And the numbers that we get are comparable only to those observed in the low Earth orbiting satellite systems, but there you have a very clean line of sight channel from you to the satellite, and we don't have that. The implications that all these distortions bear on the design of the system are that some sort of very dedicated synchronization is necessary. Otherwise, we're not going to get our time and our frequency straight, and this will cause large distortion to the signal. So if we were to summarize our distortions that account for the time variability of the channel, we could say that there are 2 types. One is the inherent variations, such as that caused by the small-scale variations of the sound speed profile, for instance, or the internal waves or the turbulence. And then there are those distortions that are induced by motion, be it intentional or non-intentional motion. The transmitter or receiver that are just suspended in water will move with the waves at about the same speed of a few or 1, let's say, meter per second. This causes Doppler shifting. One type of distortion must be dealt with through adaptive channel estimation, which is a relatively slow process. The other type of distortion needs to be dealt with through synchronization, which is a faster process because it regards the phase of the signal that I have here denoted as theta. And the message to be taken from all of this is that we have to respect the physics of the channel, because only by doing so are we going to be able to design efficient transmitters and receivers. I want to emphasize once more the major difference between radio and acoustic frequencies, which are shown here on the RF and AF scales. In the radio frequency world, we have wide bandwidths, megahertz, but they are centered around gigahertz. So with respect to gigahertz, they're not wide at all. What we have are bandwidths on the order of kilohertz that are centered around kilohertz. That is truly wideband. And that causes many distortions to the signal, but most importantly, it prevents us from directly transplanting the wealth of good methods from wireless radio communications to acoustic systems. Synchronization methods, array processing methods, and many other methods that rely on the so-called narrowband assumption may not be applicable here. So what have people done so far in terms of signal processing for high-rate underwater communications? We have first worked on the problem of so-called single carrier systems. A single carrier system has one carrier, and the message is modulated in a wide bandwidth around that carrier. In order to achieve bandwidth efficient communication in such a situation, it turns out that 3 things are necessary in the receiver design. One thing is very accurate synchronization. Another is the need to have an array of receiving sensors. And the third is the need for equalization, which will take care of multipath distortion in the system. These 3 things are put together in an adaptive algorithm and are applied to real data. Here we are looking at some samples of the signals of an 8 PSK system that were obtained experimentally. This is one of the results that showed for the first time that it was possible to detect phase coherent signals, and via equalization, synchronization, and array processing arrive at a design that is possible for an actual implementation. Over here, you're looking at a picture of the current acoustic modem that implements in itself these signal processing methods and has been realized at the Woods Hole Oceanographic Institution. The green box lists some of the current achievements that were made using this in real life experiments. We have a variety of channels here, point-to-point links that include medium range, long range, basin scale, which means almost around the globe or halfway around the globe. The vertical channel, which is an easier channel to deal with than the horizontal one because it has less multipath propagation, and where, for instance, one of the latest results includes transmission of signals from one of the deepest trenches in the ocean that lies at 10 kilometers depth below the surface. These techniques have also been applied to mobile communications so that two autonomous underwater vehicles, AUVs, can talk to one another. And they have also been extended to the concepts that involve multi-user communications. Another type of modulation detection process that we have been working on in the past several years are the multi-carrier systems. Unlike the single-carrier systems that I showed on the previous slide, multi-carrier systems take the entire available bandwidth, which is denoted by B here, and cut it up into many, many narrow bandwidths so that each is of width delta F. Then the signal modulates the carrier in each bandwidth. This is nothing new. Multi-carrier systems, and especially OFDM, which stands for orthogonal frequency division multiplexing, have been used and are being used in many of the systems that you actually have on your desks and in your pockets right now. Wireless LAN, European digital audio broadcast and video broadcast, and they are also considered to be used in the next generation of cellular phones, which is called LTE generation or long-term evolution. Unlike the radio systems, the acoustic systems that are in existence today rely on single carrier modulation and detection, but we are doing research on multi-carrier methods, especially in the form of orthogonal frequency division multiplexing as the first possibility, because this method gives us an ease of equalization. What happens is that multipath propagation results in a frequency selective transfer function of the channel, meaning that this transfer function is not flat but goes up and down. However, if we divide our bandwidth into mini pieces, then each mini piece will perceive its channel as more or less constant. And then detection is easy in each subband. Moreover, this detection can be implemented using simple FFT operations, which in fact accounts for the large popularity of OFDM methods elsewhere. So the question is, can we do this in acoustic communications as well? If we look more closely into the problem, we will notice that while equalization is easily solved, synchronization presents a real problem. If you remember the Doppler effect from a few slides ago, you remember that each frequency is shifted by an amount that is proportional to itself. Therefore, every frequency will be shifted by a slightly different amount in a system such as an acoustic system that is inherently broadband. where not all the frequencies are more or less equal to the carrier frequency, but they're all different. So the question is, how do we efficiently solve the problem of synchronization, where we have to synchronize a potentially large number of carriers? This K could be maybe 1024. We have worked on the design of various synchronization algorithms and eventually taken them to testing in a real environment. What I'm showing here is an experimental result of transmission over 2.5 kilometers in this acoustic bandwidth, where we managed to perfectly reconstruct the transmitted signal, even though the received signal looks like this. It has gone through a time-varying channel. This particular result speaks to the possibility of achieving bit rates as high as 30 kilobits per second at minimal computational complexity that is dictated here by the FFT operations only, plus some clever way of doing synchronization. And this is one of the areas where research is very active these days, and it is for the future to see whether we are actually going to move on with real-time implementations of these new techniques. I would like to talk a little bit now about a different and upcoming topic of underwater networks. If we are happy with the point-to-point signal processing systems that we have, then the next question is obviously, can we put these things together and form an underwater network? And the answer is yes. This picture actually shows, illustrates a recent expedition that involved several underwater vehicles equipped with underwater acoustic modems that were dispatched on a search mission in the very deep sea around this mid-Atlantic ridge. It is possible to form a network, but to this day we have no routinely operational networks, and it is an open question of how to design efficient networks. The applications, however, are calling for the deployment of various underwater networks, be it in industry, be it for climate recording, be it for search and mapping of the ocean, or just pure sciences. We would like to have two types of networks. We would like to have sensor networks, so sensors perhaps deployed on the ocean floor to record some data and transmit it back to the surface. And these networks would need to be deployed there for a long period of time without having to go in there and change their batteries very often. So we need some kind of energy efficient networking. And another type of networks which would involve cooperating autonomous vehicles. So we need to have some system intelligence that will be supported by wireless communications, and may also in turn have to support wireless communications in this very difficult propagation channel. The types of nodes that we will have in these networks are various. We may have fixed and mobile nodes. We may have requirements for low and high bit rates, and the matching requirements for high and low reliability. If you are transmitting a signal in an oil field that says shut the vent, it has to be received with very high reliability. If you are sending a video of a moving fish, well, never mind if you make some mistake, you need a high rate. You don't need that higher reliability. Some applications call for real-time transmission. Some do not care about real-time transmission. And finally, these future systems will perhaps be acoustic only, or they will be integrated into larger scale systems such as ocean observatories that will have an infrastructure permanently mounted on the bottom of the sea, and wireless communications will serve as an extension. So here I have a little illustration of the possible types of future underwater networks. we may have, I'm not saying that we will, this is just a drawing, we may have centralized networks that will follow the paradigm of cellular systems on land, where each base station is serving its own footprint of nodes, and it's talking to another base station through a different than acoustic link, maybe radio on the surface or cable on the bottom, so that this different station has its own users. Another type of networks are the decentralized networks that will follow the paradigm of ad hoc, multi-hop networks that we have in the radio world. Here, there are no base stations, there is no infrastructure. The nodes alone are responsible for setting up the connections, relaying each other's messages until they reach the destination. And of course, if we are going to have these two types, maybe in the acoustic channel we would also like to consider hybrid types that will borrow from both worlds, from the cellular and the ad hoc, to get something good in the end. Because remember, we are talking here about a propagation medium where power is limited and bandwidth is limited. And when it comes to networks, these two facts actually are building a strong case for networking. Remember, the shorter the distance, the lower the power, always in any system, including radio systems. But here, also the greater bandwidth. So if I have one link of distance d, I could perhaps transmit all across this link, or I could transmit by relaying from one node to another. And as it turns out, because of the fact that the acoustic bandwidth depends on the distance, we stand to gain a lot by relaying instead of by transmitting just in one hop. This is just an illustration of total consumed energy as a function of the number of hops. And clearly, you see that there is some kind of a minimum in this optimization business. So there is the best number of hops that one could choose for some link. Now, if we go at lower power over shorter links, that will also reduce the amount of interference. There will be fewer collisions of data packets coming from different nodes. And because the bandwidth is greater, the duration of data packets will be shorter in terms of seconds, not in terms of number of bits, in terms of seconds, which will even further lower the chances of packet collisions. And we will get to some sort of efficient networking. In order to get there, we have to think of the design of underwater networks or protocols for networks on all layers of the network architecture, from signal processing on the physical layer to power control that will allow us to exercise these principles, to channel sharing, or the MAC, the medium access control, to routing, and even further up. The main problem in doing this is the fact that these networks have to deal with high latency. Remember, 1500 meters per second. The sound is very slow. Unlike in the radio networks where packets go almost with no delay, here there is a visible delay in transmission, and that in turn may cause collisions and call for redesign of the existing protocols. On top of that, we have this very difficult physical link where outages may occur, so that retransmissions will be necessary. And this protocol design, once done, has also to account for the fact that there is limited power budget and that the bandwidth is very restricted. And with that, I would like to conclude my presentation just by outlining a list of open problems. We don't have to read through this list. You're welcome to print it out, take it home, and think about it. But let me just say that there are the green, the yellow, and the red levels. The green level being the communications link, where problems remain open, especially on statistical characterization of the channel, which we don't know. The design of transmitter methods, such as adaptive modulation, power control, spectrum shaping, coding, and the design of receiver techniques that involve adaptive signal processing, model-based signal processing, but model-based signal processing will have to feed off of channel modeling. And all of this, of course, in single carrier and multi-carrier and single input and multi-input, multi-output configurations. The yellow box is where we are doing some research, but there's much more to be done. When it comes to networks, we need efficient and scalable protocols that can be scaled up in area on all layers of the network architecture. We need methods for frequency and time reuse, topology control of a network. Remember, we don't know what are the best topologies. And we also know very little about the fundamental capacity limits of these networks. And the red box controls the higher level, final stage of system integration and system optimization, where communications will have to be integrated with other functions of the system, such as localization, navigation, and the ultimate application of the system, if we are going to squeeze what we can squeeze from this channel that has such a limited bandwidth and difficult propagation. So we will need not only the cross-layer design, as it is called in the networking world, we will need more than that. We will need integration of functions that go all the way from the application to communications and back, if you want, because communications will serve the application, but we will have to be clever and somehow close the loop, and depending upon the application, design the most efficient communication method for that application. And I would like to conclude with this and answer any questions that you might have.
Thank you very much.